right, welcome back. Chapter 4. Chapter 4 is going to begin the process of undoing what we have done all year long. So what have we done, or most all year long? What have we done for the most of the year? We found the derivative. So we started with the function. We came up with the derivative, or the rate of change. What we're going to do is give you the derivative, and you're going to come up with the original function. So we call this integration, or the antiderivative. So before we go ahead and find and look at the antiderivative, I want to remind us, how do we find the derivative first? So if you recall, to find the derivative, we called it f prime of x. We found the derivative of x squared, which would multiply the 2, the exponent to the front, and then we decrease the exponent by 1. So we got 2x to the first. Derivative of 4x was 4, because we had it to the first. 1 times 4 gives us 4. X to the 0, which was 1. And then minus the derivative of 5, which is 0. So our derivative was 2x plus 4. So if we start with that derivative, how do we get back to the original function? So we're going to undo that process. So what did I do? I multiplied the exponent to the front, and I decrease the exponent by 1. So to undo that, I'm going to increase the exponent by 1 and divide by that new exponent. So if I take my 2x to the first and I increase the exponent by 1, I get 2x squared divided by that exponent, which is 2. 2 that I'm going to add, I'm going to take my 4. It was 4x to the 0, remember? So I'm going to increase that exponent by 1. I'm going to divide by that new exponent. That's all the value of all the terms that we have. So we're going to end up with x squared plus 4x. And you're going to ask yourself, well, wait a minute, that's not exactly the original function, is it? Oh, no, it's not. We have this problem here, don't we? This negative 5. So what we do, we don't necessarily know what number was out there. So at this point, what we're going to do is we're going to put a plus c. And that c is going to represent a constant. So some value c. We're going to see that c is a very fluid c. We'll talk about that in the days to come as well. So here's our critical information. A couple things of critical information here, I suppose, today. Integration means the antiderivative. So I can ask you to find the antiderivative. I can ask you to integrate. To integrate, we're going to add 1 to the exponent, and we're going to divide by the new exponent. In order to find the antiderivative at this point, we have to be in polynomial form. If you recall the power rule for derivatives, if we gave you f of x for the power rule, it had to be in polynomial form. If I gave you x plus 1 over x, what we did was we broke this up first. So 1 plus 1 over x, and then we wrote this as x to the negative first. So we wrote it as 1 plus x to the negative first. So it's got to be in this polynomial looking form. So in a polynomial looking form, it just means that we have all our x's in the numerator and they're all separate terms. That's what I call polynomial looking form. All right. Some things that we're going to see, some symbolization. We're going to see this elongated s. That's very important to us. That tells us that we're going to integrate. That's our integration symbol. We have the function that we're integrating. We call that the integrin. And then, very important as well, we have this dx. This is going to be the variable of constant. Whatever this variable is here tells us what variables we have to have over here. They all have to match. So if we have x's here, it has to be x's here. If we have y's here, this has to be a dy. If we have z here, these all have to be in z form. So very important as well. As we get into it, we're going to start changing things around. For the first few days here, it'll all be nice and clean and neat for us. We also don't want to make sure that we forget the c. Don't forget the c, that constant at the end at this point. A little bit of notation. We use a capital F of x to show that we took the antiderivative of something. So if our derivative, our original function was 2x plus 4, then f of x is going to be that original function Little f would have been the derivative. Not major with this information here, but this book likes to use that f, the capital F, showing notation that we took the integration, the antiderivative of the function. So let's go ahead and look at some examples. We got just a few of them here. Shouldn't take us a miserable amount of time to get through. So we're going to integrate 3x to the fifth, blah, 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 blah. So I'm going to go ahead and increase the exponent by 1 and divide by that new exponent. So I get 3x to the sixth over 6 plus, I'm going to increase the exponent by 1, so I have 1/2 times that. I can leave the 1/2 out there. I can increase the exponent by 1 and divide by that new exponent. 6x to the second, 6x squared gives us 6x to the third over 3 plus 5x squared over 2 minus 2x, and then we don't know what constant was out there, so plus c. So our function, we can go ahead and simplify this. We have x to the sixth over 2 plus x to the fourth over 8 minus 2x to the third plus 5x squared over 2 minus 2x plus c. Now, the question is, do we have to find a common denominator with this? You can. I'm not going to require us to do that, but we could find a common denominator there as well. We would leave the c out by itself 99.9% of the time. We normally do not deal with that c when we find a common denominator. So if you wanted to find the common denominator, that would be 8. So we would have 4x to the sixth plus x to the fourth minus 16x to the third plus 20x squared minus 16x, and then we put the plus c at the end. Integration for our next problem. So again, it has to be in polynomial looking form, so we cannot have a rational function at this point in time. So we're going to break this up into x squared over x plus 3x over x minus 2 over x dx. I can go and clean those up as well, so I get x squared divided by x gives me x plus 3. Then we're going to bring that to the top as 2x to the negative first dx. Notice I still have this elongated s, this integration symbol. We want to make sure we put that integration symbol on there until we actually go ahead and integrate. We also don't want to integrate part of it, not all of it, within our problem, because then we get confused on it. Did I integrate that or did I not integrate that? So we can go ahead and integrate this now. So the integration of x, that gives us x squared over 2. Integration of 3, we get 3x. Integration of negative 2x to the negative first. So I'm going to take increase my exponent by 1, sorry. We get 2x to the 0, divided by that exponent, which is 0. That's a problem, isn't it? So let's think about this 1 over x, this 2 over x. Think about what we took the derivative of. What did we take the derivative of something that gave us 1 over x? What was that? What was that? How about the natural log of x? The derivative of the natural log of x is 1 over x, isn't it? So we know that we can come back here and we don't get this over 0. We know that's not possible. So we have minus 2 natural logs. Remember, we have to take the natural log of a positive number, so the natural log of the absolute value of x plus c. And that's going to give us then this integrand, or this derivative, if we took the derivative of this. All right? All right, a couple more examples. They get kind of nasty and ugly if you want. We're going to go ahead and break this up. I would go ahead and change your radicals to fractional exponents, so x to the 1/3. Breaking this up, x to the 1/3 over x, that's 1 over x to the 2/3, isn't it? Plus 4, I'm going to break 4x over x, plus 3x dx. Bring this x to the 2/3 to the top as a negative exponent. So we have x to the negative 2/3. Again, I'm not going to start integrating, even though I know how to integrate that. I'm going to wait until I can do it all at one time. So now I can go ahead and integrate. I have x to the 1/3, and I'm going to divide by 1/3. Some of you probably already see that. Hey, that's just multiplying by 3. Of course it is. You can. Integration of 4 is x, and then 3x gives me 3x squared over 2 plus c. Again, we can clean this up a little bit. F of x is going to be 3x to the 1/3 plus 4x plus 3x squared over 2 plus c. Again, multiple choice, you could see it like this. You could see a common denominator. Several things we could see with that. Our last example, just cleaning this up a little bit. Notice in our denominator we have 3x, the quantity to the third. So that's why we have to be very careful, because you have to multiply that 3, take that to the third power as well. So we're going to have 27x to the third when I go ahead and distribute that cube. And here I have x radical x. So remember, x, or the square root of x, is x to the 1/2. I can add those exponents, so I get x to the 3/2 dx. Again, I'm going to bring that x to the third to the top. I'm going to leave that 27 down there. So I'm going to write it as 2/27 x to the negative third plus x to the 3/2 dx. I can go ahead and integrate now. So I have 2x. Integrating, I get, adding 1 to the exponent, negative 2 over a negative 54. So I'm going to divide by negative 2. I already have a 27 down there, so I get a negative 54. Plus, here we're going to increase the exponent by 1, so we get 5/2 divided by 5/2 plus c. So to clean this up just a little bit, if you want, negative exponent, that can go back to the bottom. So we get negative 2 over 54x squared. And then my 5/2 I can flip and multiply, and I get plus 2/5 x to the 5/2 plus c. And that gives me my original function. So that gives you an introduction of integration, the antiderivative. We will continue, and we'll work quite extensively with integration here in this first section. We have a lot of rules and some trig to get through, and then we'll also be able to find that big C later on. So the big idea here today, make sure it's in polynomial looking form. We're going to increase the exponent by 1, divide by the new exponent. And don't forget the C. Good luck, enjoy, happy anti-deriving.